Hello my friends and welcome back to the You Can Do TV channel.
Innovation and human expertise converge at GWF Mengele GmbH, revealing the complex process behind high-quality sheet metal production. At the very start, the journey of sheet metal transformation begins with a thorough preparation of the raw material. The initial stage involves precise measurements and inspections to ensure the material meets the required specifications. Operators take note of even minor deviations, recognizing that every detail affects the final product. Each decision made at this early stage resonates through the entire production process. The anticipation in the workshop grows as the prepared sheets await further machining. Subsequently, the material undergoes cutting processes, where advanced machinery slices the metal sheets to the desired dimensions. This step is crucial as it sets the foundation for the subsequent forming operations. The cutting machines operate with relentless rhythm, translating careful planning into tangible results. After cutting, milling and turning operations open the next phase, shaping precise edges and contours. CNC milling machines engage in intricate movements, producing grooves and features that will define the final assembly. Operators monitor feeds and speeds, adjusting settings to maintain perfect alignment. Sharp edges are refined, and surfaces are smoothed, ensuring both functionality and aesthetics. Each machine detail reflects both the machine's capability and the worker's oversight. The final stage involves assembly, where the individual components are thoroughly joined together to create the finished product. Witnessing the coordination between machines and workers underlines the efficiency and dedication behind each assembly. Every completed product carries the mark of expertise and careful orchestration.
In Europe's energy hubs, enormous structures depend on ropes engineered to handle extreme forces. Hendrik Vader Group produces steel wire and fiber solutions rooted in centuries of expertise. Production begins with design and testing, where ropes undergo proof load and breaking load trials reaching 1,250 tons. The sight of massive machinery pulling with relentless strength underscores the trust placed on these products. Each strand is evaluated so that the entire rope can carry its assigned duty without compromise. Spooling and reeving prepare them for operational use. The sheer tension during testing inspires awe, reminding us that safety offshore relies on unseen details. Inspections and certifications follow, ensuring reliability. Technicians document every parameter, issuing clear evidence of compliance. With 3,000 items in stock, availability remains constant. Each stage shows engineering discipline, meeting real-world demand. Beyond production, these ropes stand as guardians of heavy lifts, towing, and mooring in some of the harshest environments. Heavy repair tasks demand structured methods, and installing a TC rotor highlights this discipline. The scale of the rotor alone creates an impressive sight. The process starts with careful alignment of the rotor to its housing, ensuring that seating is correct. This alignment moment feels tense yet controlled. Bolts are then tightened gradually, securing the heavy component into position. Next, torque checks confirm stability across all connections. Finally, the assembly undergoes inspection, verifying that the installation is safe and reliable for continued turbine operation. When a pump reaches the workshop floor, It does not immediately look like a machine ready to deliver power. Layers of use, oil, and age cover its surface, signaling the need for a thorough restoration process. It feels almost like watching strength return to a machine piece by piece. There is a quiet anticipation as the restoration team gathers around the unit. The site carries a mix of respect and responsibility, because every pump restored will soon power vital systems again. The process begins with complete disassembly. Technicians unfasten bolts, remove end covers, and carefully lift out shafts, bearings, and seals. Each part is organized systematically, preventing confusion later. The methodical rhythm of dismantling shows how experience guides every movement. The sound of tools striking metal adds a steady background to the workshop atmosphere. Every removed piece tells a story of long operation hours and wear. It is fascinating to realize how many hidden details remain inside until the machine is opened. Once the pump is stripped, cleaning takes center stage. Degreasing fluids, brushes, and air jets remove dirt and hardened oil. Stubborn residues are blasted away with specialized tools, leaving the metallic surfaces exposed. The sight of shining surfaces emerging from grime carries a sense of renewal. It almost feels like the pump is breathing again after years of labor. Even the smell of solvents in the air reminds everyone that renewal is underway. At this stage, patience is essential, because every corner must be free of debris for the pump to operate flawlessly. After cleaning, each component undergoes inspection. Worn seals, scratched pistons, and damaged bearings are discarded. New parts, manufactured to strict tolerances, replace them. The contrast between worn parts and replacements highlights the importance of maintenance. The gleam of new components next to tired old ones is striking. You can sense the confidence in technicians' movements as they fit replacements. Each substitution feels like giving strength back to the heart of the system. The next stage is reassembly. Shafts are positioned within housings, bearings are pressed in, and seals are fitted into grooves. Tightening sequences follow torque guidelines to ensure secure connections. This step demands focus because one misaligned piece can affect the entire pump. The process resembles putting life back into an intricate puzzle. Every tightened bolt feels like progress toward revival. The workers share brief nods of approval as each part fits smoothly, reflecting teamwork in silence. Following mechanical assembly, functional tests are performed. Technicians rotate the shaft by hand, feeling for smoothness. Hydraulic test rigs then simulate operating pressures, verifying that internal chambers seal properly and that flow is consistent. The hum of test benches assures that performance is returning. The moment of testing always carries tension and relief once results are clear. Hearing the pump respond properly brings satisfaction to the entire team. Even the smallest vibration is noted, proving how attentive the technicians remain. With performance confirmed, the pump is prepared for refinishing. Manual spray painting covers the housing with a protective layer, restoring not only durability but also appearance. Fresh paint makes the pump look almost brand new again. The final spray of paint feels symbolic, sealing the work with both function and pride. Steel fabrication for a spillway begins with profile bending, shaping strong plates and beams into structural forms. Next comes cutting and welding. Joining each section with accuracy, assembly follows, turning components into a unified frame. The scale of this build feels truly commanding. At the heart of heavy industry, the forging of a massive roll begins with raw steel heated to a glowing state. The atmosphere is charged with intensity as the furnace brings the ingot to forging temperature. The brightness of the metal radiates sheer strength, creating a dramatic scene in the workshop. The heated block is moved to the forging press, where enormous force begins shaping it into the foundation of a rolling mill roll. Each strike compresses the grain structure, enhancing durability and toughness. It is striking how every impact leaves a clear trace of transformation. Step by step, the steel elongates and thickens in the right places, guided by experienced operators. Intermediate reheating keeps the steel workable, preventing cracks while allowing continuous forming. Forgers ensure symmetry through repeated pressing and rotation. The rhythm between machine and operator feels almost like a dialogue of power and control. The weight of 2,600 kilograms demands exact handling throughout the entire process. As the rough form emerges, finishing presses refine its cylindrical shape. The roll gradually takes on the dimensions required for industrial performance. At this stage, the scale of engineering truly becomes visible. The heat, the weight, and the relentless force combine into a spectacle that commands respect. The combination of heat, pressure, and expertise defines the product's reliability. Once complete, the forged roll stands as a critical part of rolling mill operations. At first glance, the Byler Bimeric BM 4500 inside Dawdite GmbH might appear like just another industrial machine, but the scale of its operations tells a different story. Each movement is orchestrated to bring together stamping, forming, and assembly into one continuous flow. It is striking how such a compact unit manages tasks that would normally require multiple machines. The process begins with feeding raw strip material into the machine. The strips are guided into position with high consistency, ensuring that every following stage has a solid foundation. The rhythm of the feeding section gives the impression of unstoppable progress. Stamping comes next, where high-tonnage presses shape the metal strips into required geometries. Holes, slots, and outlines are punched with force and speed, creating blanks ready for forming. The sharp sound of each impact highlights the raw power involved in metalworking. Forming stations then bend and shape these blanks into three-dimensional parts. Each tool strikes with accuracy, folding metal into its final contours. Watching flat material gain depth and dimension adds to the sense of transformation. Assembly is integrated directly into the cycle. Components such as springs or connectors are placed, joined, or riveted as needed, all without removing the workpiece from the system. The efficiency of combining processes reduces downtime and maximizes throughput. Final inspection ensures that every finished product meets the intended specifications. Cameras and sensors track alignment, dimensions, and overall quality before parts leave the machine. This closing stage shows the seamless blend of mechanics and electronics. The Bimeric BM 4500 represents a modular concept where multiple processes coexist in harmony. By condensing stamping, forming, and assembly into one system, it provides flexibility for customized production runs. Such integration reflects not only technical capability but also industrial foresight. The sight of raw steel being shaped under immense pressure is always striking, and in this case, the forging of a shaft begins with a massive billet. It is placed beneath the jaws of a hydraulic press rated at 3,000 tons. The sheer power of this equipment ensures that each blow compresses the metal, driving out voids and aligning its internal structure for strength. One can almost sense the energy locked inside the glowing steel as it begins to yield to force. The initial stage involves upsetting the billet, shortening and thickening it to prepare the stock for elongation. This process distributes material evenly, laying the groundwork for the long shaft form that will emerge. The hammering effect of the press ensures high density, which is essential for components that must withstand rotational and bending loads. At this stage, the sound of the press striking steel resonates through the workshop, leaving no doubt about the force involved. Observers often remark on how the glowing billet almost seems alive as it changes shape with each strike. Next comes elongation, where repeated pressing stretches the billet into a longer, narrower shape. The workpiece is reheated periodically to maintain plasticity, avoiding cracks that could form if the material cooled too much. Each cycle of heating and pressing refines the grain structure, creating both toughness and resilience in the finished shaft. It is impressive how the glowing metal gradually transitions into a recognizable cylindrical form. The operators demonstrate great coordination in moving the shaft quickly between furnace and press, ensuring continuous progress. Once the general length is achieved, the forging continues with forming operations that define the step sections along the shaft. Shoulders, flanges, and transition zones are pressed into shape, ensuring that functional features are integrated directly in the forging rather than being machined entirely later. This not only saves material, but also strengthens the transitions by maintaining grain flow. The repeated reorientation of the shaft under the press shows the precision required in every stroke. Each adjustment by the workers highlights their understanding of both material behavior and machine capability. The nearly finished shaft is then normalized by controlled cooling, which relieves stresses accumulated during forging. This thermal process ensures dimensional stability and prepares the steel for subsequent machining. Without this step, distortions could occur later in service. Even as the glow fades, the steel retains a sense of power and endurance. The gradual cooling process is just as critical as the pressing itself, influencing the performance of the final part. The forged shaft is finally inspected for straightness and dimensional accuracy before moving on to machining and finishing. By forging on a 3,000-ton press, the resulting part achieves mechanical properties far superior to those of a cast or welded piece. It is remarkable to consider how every stroke of the press contributes directly to the reliability of the final shaft. The finished component will eventually take on vital tasks, carrying loads and transmitting motion in demanding environments.
The scale and engineering of Howden's WRVIT 580 inspires awe as teams manage the assembly of this massive screw compressor. The process begins with positioning the heavy base frame, establishing stability for subsequent components. Rotor shafts are then installed, central to the machine's function. Housing sections are aligned and secured, followed by the installation of the oil injection system. Finally, control and monitoring units are connected. Observing the coordination required for such a large machine highlights the dedication and expertise of the workforce. At Vitkovits Steel, the immense energy of steelmaking is evident as workers and machines coordinate on an industrial scale. Heating massive steel slabs in the furnace marks the opening stage, bringing them to the temperatures necessary for shaping. The glow of molten steel emphasizes the power contained in each slab. As they leave the furnace, the slabs enter the rolling mills, where successive passes gradually reduce thickness and extend length. This action transforms rigid blocks into workable heavy plates. Following rolling, cutting operations open the next phase of work. Machines slice the steel into sheet piles or custom shapes, guided by precise measurements. The force and speed of cutting highlight the combination of equipment strength and operator skill. Once cut, the plates undergo inspection and verification. Dimensions, surface quality, and alignment are assessed, confirming that every piece meets industrial standards. Even minor imperfections are corrected, reflecting the team's commitment to reliability. Finally, the finished plates and shapes are arranged for storage or delivery. Handling and organizing such massive components requires coordination and expertise. Seeing this synchronized workflow conveys both the intensity and dedication required to produce steel on a monumental scale, reminding viewers of the human and mechanical effort behind Europe's infrastructure. Forging at Shanxiliang demonstrates how human expertise and heavy machinery converge to produce components critical for global industry. Raw billets are preheated in high-temperature furnaces, reaching temperatures that make the metal malleable for shaping. Once heated, the billets enter the primary forging presses. These machines shape the metal into rough forms of flanges or rings. The sight of massive presses in motion evokes respect for both human skill and mechanical power. Each press exerts immense force, a testament to the collaboration of human and machine. Hydraulic pressures are calibrated for each batch according to the billet's composition and size. The metal's resistance to compression is measured continuously to prevent defects. Sensors track deformation rates in real time to ensure consistency. The force and energy required at this stage emphasize the power and precision controlled by the operators. Depending on the specifications, hydraulic or mechanical presses apply repeated compressions, gradually refining the shape while reducing internal stresses. Temperature gradients across the billet are monitored to prevent microstructural inconsistencies. Skilled operators adjust press speed and stroke length in real time, responding to variations in billet density. Adjustments are made dynamically, reflecting the experience and intuition of the operators. This phase highlights the combination of machinery capability and human supervision, as adjustments are made to ensure the product meets design tolerances. The rhythmic compression sequences create uniform grain flow, improving mechanical properties. Watching this process evokes admiration for the skill and timing involved. Cooling rates are carefully controlled between press cycles to maintain microstructural consistency. Following primary forging, the components are transferred to secondary forging. Here, excess material is removed, and dimensions are brought closer to the final specifications. The trimming stage emphasizes the importance of uniformity and exact measurements. Forged surfaces are examined for uniformity and structural integrity. The repetitive, coordinated actions of both machine and operator reflect the dedication to producing components capable of withstanding industrial demands. Even subtle imperfections are addressed immediately, showing rigorous attention to quality. Each inspection reinforces the reliability expected in industrial applications. Heat treatment is then applied where necessary. Components are normalized, quenched, or tempered to enhance mechanical properties such as hardness, strength, and toughness. The controlled heat cycles bring out resilience and durability in the metal. It is fascinating to observe the transformation of the metal under precise thermal control. Witnessing the metal change characteristics under controlled heating and cooling underscores the transformation that raw materials undergo. These changes illustrate how raw energy becomes structured strength. Observing the entire workflow, from material preparation to final inspection, inspires admiration for the combined expertise of workers and the engineering of heavy forging machinery. Every flange or ring carries the imprint of controlled force, skillful handling, and careful orchestration that ensure the final product meets stringent operational requirements. The seamless integration of heat, pressure, and human oversight highlights the remarkable craftsmanship behind each component produced. The launch of Arklow Abbey captures the culmination of extensive shipbuilding effort at Ferris Smith. Preparations begin with final inspections of the hull and systems, ensuring seaworthiness. Support structures are adjusted, and the vessel is carefully positioned for descent into the windshoulder deep. Watching the ship gradually slide into water evokes admiration for engineering skill and coordination. The launch signifies both completion and the promise of journeys ahead. Our Earth. The workshop is filled with focused activity as the Tornos Swiss Deco 36 TB bar turning center is set up for production. A metal bar is loaded into the rotating guide bush, with the standard workpiece measuring 300 mm in length. Operators ensure it is aligned perfectly along the B-axis turret, ready for multi-axis machining. It is remarkable to see how compact yet powerful this machine handles precision work. Machining begins with the first cut along the bar's surface. The Swiss Deco 36 TB supports up to 5 simultaneous axes, allowing complex geometries to be formed in a single cycle. The torque of 53 Nm on both spindles ensures that even dense materials maintain consistent cutting performance. Deep hole drilling for internal threads is performed using the Z2 axis and integrated fluid module, highlighting the machine's advanced capabilities in orthopedic components like intramedullary nails. Operators monitor spindle speed, feed rate, and tool engagement closely to optimize surface quality. The precise synchronization of tool movement and axis rotation draws attention to the machine's remarkable engineering design. Rotating tools are employed for contouring, threading, and drilling, with 36 out of 57 available tool positions capable of rotation. Watching the coordinated movement of multiple tools and axes emphasizes the efficiency achieved in a compact footprint. The machine's long part option accommodates 600 mm workpieces, demonstrating flexibility for varied production demands. Heat exchanger and high-pressure fluid modules maintain optimal temperature and lubrication, protecting both machine and tool while ensuring consistent performance. Operators occasionally adjust parameters to compensate for material variations, ensuring quality across each workpiece. Observing how quickly the machine completes intricate operations adds a sense of industrial fascination. After machining, the workpiece is inspected for dimensional accuracy, surface finish, and thread integrity. Tolerances are verified using specialized gauges, and minor adjustments are made if necessary. Finished IM nails exhibit flawless internal threading and surface smoothness, ready for demanding orthopedic applications. The seamless integration of automation and operator oversight makes each nail a testament to technical skill. It is inspiring to witness such efficiency combined with thorough attention to detail. The Swiss Deco 36 TB integrates high-end technology with user-friendly operation. Its autonomous fluid management and high-pressure pump configuration allow continuous production with reduced downtime. Machine design emphasizes compactness, rigidity, and thermal stability, enabling precise machining on challenging materials. The combination of 5-axis control, high torque, and intelligent tooling underscores Torno's commitment to innovation in bar turning centers. The Swiss Deco 36 TB is not just a machine. It represents a high-performance production solution capable of delivering reliable, accurate components for the medical and dental industries. Rise in the construction hall. Large hull sections are assembled and aligned, forming the backbone of this futuristic vessel. Engineers and technicians collaborate to install advanced sensors, navigation systems, and automated control modules. It is fascinating to see such a complex ship built for autonomous operation, blending engineering, and innovation. Welding teams reinforce the structure, while electrical teams integrate computing hardware, ensuring both durability and intelligence. Observing the ship gradually transform from steel plates into a self-navigating vessel sparks excitement for the future of maritime technology. Steel dominates the industrial hall as raw materials arrive for processing. The flow from raw ore to ready-to-use steel illustrates the scale, complexity, and expertise behind industrial steel production, showing how each carefully managed step contributes to materials that support countless industries and infrastructure. Iron ore and coal are prepared, with the coal transformed into metallurgical coke in high-temperature furnaces for 16 to 18 hours. The resulting coke and sintered iron ore are loaded into the blast furnace, where hot air and auxiliary fuels like pulverized coal and natural gas drive chemical reactions, producing molten pig iron. It is striking to see how such massive components are coordinated to create liquid metals safely. Operators constantly monitor temperature and chemical reactions, ensuring the process remains stable. The roar of the blast furnace adds an awe-inspiring sense of scale. After tapping, molten iron undergoes desulfurization, then is poured into a converter with scrap metal. Oxygen is blown in to reduce carbon and phosphorus, transforming it into steel. Alloying elements are added to give the steel specific physical and chemical properties. Observing the transformation highlights the technical skill required to maintain exact chemical composition. The liquid steel is then cast continuously into slabs, which solidify and are cut to the required lengths. These slabs enter rolling mills, where they are processed hot to produce thick sheets or strips. Hot-rolled products are cooled, coiled, and inspected before being sent for further processing or sale. It is fascinating to see enormous slabs shaped with precision and efficiency. Cold rolling follows for applications demanding high surface quality and tight tolerances. Coils are pickled, annealed, and work hardened to adjust mechanical properties, then cut to size. Some are further treated with electrogalvanizing or hot dip galvanizing to prevent corrosion. Watching each stage demonstrates the combination of heat, force, and control needed to produce durable, high-performance steel. Finally, finished products are labeled, packed, and dispatched via an integrated supply chain. Modern monitoring systems ensure quality and traceability throughout. Every slab and coil tells a story of skill and coordination. The workshop fills with heat and sparks as steel pipes are prepared for hot induction bending. Operators position the sections carefully, aligning them for precise curvature. The induction coils heat-targeted areas, making the metal pliable. Skilled teams monitor temperature, bending angle, and pipe integrity, ensuring each bend meets structural requirements. It is impressive to see steel flow under controlled force. Heh. The scale of nuclear construction is on full display as Akuyu NPP Unit 1 prepares for a milestone. The reactor pressure vessel, towering and heavy, arrives at the site. Massive cranes position themselves for the lift, their movement slow but steady. The anticipation in this stage feels intense. The vessel is hoisted carefully into the reactor building. Engineers guide alignment, ensuring exact placement on its foundation. Every adjustment carries enormous responsibility. Once secured, the structure marks progress toward clean energy. The achievement resonates far beyond the site. Innovation in drilling takes shape with the ISCAR CHAM IQ drill cartridge system. Production begins with tool body preparation, ensuring the core can accept cartridges securely. At this stage, the foundation of accuracy is built. Next, cartridges are inserted, their geometry designed for efficient chip evacuation. Each insert is locked in place, without the need for screws, speeding up assembly. The simplicity of this design feels remarkable. The completed tool undergoes inspection, confirming alignment and durability. Finally, it is ready for demanding drilling operations. The balance of strength and efficiency is striking. This process highlights engineering skill turned into practical results. The production of a crankshaft at ALFING represents an industrial process shaped by strength and experience. It begins with closed die forging, where heated steel ingots are transformed under counterblow hammers and powerful presses exerting up to 500 tons of force. The scale of energy at this stage is immense, and every strike reshapes the raw block into a recognizable form. The thunderous rhythm of hammer blows conveys a sense of raw industrial might. Watching the red-hot steel being compressed is both intimidating and fascinating at the same time. Pre- and intermediate machining follows, performed on advanced CNC turning and milling machines. Integrated measurement systems ensure geometry is maintained during rough shaping. The combination of power and accuracy feels impressive here. Each transition between machines shows how seamlessly the process is connected. The interplay between digital control and heavy metal cutting underlines how tradition and technology coexist. Heat treatment is next, applying induction hardening or stroke peening to increase surface strength. Each method enhances durability against fatigue, an essential property for engine performance. The glowing steel during hardening leaves a striking impression of resilience. It is a visual proof that durability is engineered, not just expected. Material testing accompanies these steps, including magnetic particle inspection, bending and torsional fatigue tests, and residual dirt analysis. These controls secure reliability for every unit. The thoroughness of verification truly inspires confidence. Finishing operations then refine the part. Multi-stage machining, shot peening, and dynamic balancing bring tolerances down to as little as 1/1000th of a millimeter. Laser coating and automated measuring systems finalize quality checks. At this point, the crankshaft carries both engineered precision and physical strength. The exactness of these final touches gives the component a sense of completeness, ready to serve in engines worldwide. In the clean room, washing, preservation, and packaging are conducted to prepare for shipment. Each shaft leaves the factory ready for installation. Hanapatch. A single aluminum ingot begins its journey with an immense blend of scrap and pure metal sourced from many places. The ingot department ensures these inputs match the alloy specifications customers demand. It is striking how so many origins merge into one material. In the first stage, recycled scrap is melted in large furnaces, then combined with pure molten aluminum in casting furnaces. The glow of molten metal signals both heat and promise. Next, aluminum flows into electromagnetic casting pits, where fields shape it without a physical mold. This method creates ingots up to 30 feet long and 44,000 pounds. Their scale feels almost beyond measure. Once solidified, they move toward rolling. Industrial manufacturing often carries an atmosphere of both power and precision. In this environment, roll forming demonstrates how metal can be reshaped through a sequence of controlled steps. The process balances engineering design, mechanical force, and continuous monitoring. It is impressive how raw coils transform into functional profiles with such consistency. The sequence begins with engineering and tooling development. Specifications are programmed into machines so that each mill run follows exact dimensions. This stage defines how every later step will unfold, ensuring that the part's geometry matches expectations. Production starts with coils of steel, stainless steel, or aluminum. The material is uncoiled and advanced through piercing dies, where holes, slots, or notches are introduced. The clatter of punching tools brings an immediate sense of industrial rhythm. After cutouts are made, the strip enters successive roller dies. Each pass adjusts the shape slightly, minimizing internal stress while forming the desired cross-section. The gradual shaping under controlled force reveals the efficiency of the method. When the target profile is reached, a cutoff die trims pieces to length. Parts then undergo inspection for dimensional accuracy and surface quality. Some mills run galvanized steel into complex profiles such as wall studs, requiring additional passes. In certain cases, multiple strips are rolled together into one component, eliminating welding. Such integration feels remarkably efficient. Where joints are needed, robotic welding systems execute uniform connections, while resistant spot welding employs electrical heat to bond sections. Both methods allow high production rates without compromising strength. Finally, automated assembly units may complete the component. Screw machines apply thousands of fasteners daily at set torque values. The scale of repetition here highlights how automation extends human capability. Each finished profile is prepared for its next role in construction or manufacturing. A single touch of a button can set an entire system in motion, and in this workshop, that moment begins the path of shaping steel into flawless rings. The first sight of glowing steel entering the system already builds anticipation for what follows. The sequence starts with automatic positioning. The machine clamps the heated billet securely and aligns it between mandrel and main roll. Sensors confirm alignment, ensuring the billet sits correctly before rolling begins. It is impressive how technology reduces human effort while keeping accuracy intact. Next comes the rolling phase. The main roll presses forward, elongating the billet into a circular form while the mandrel supports its inner diameter. Hydraulic systems apply controlled pressure, allowing the ring to expand smoothly to the desired size. The rhythmic motion of the rolls creates a sense of steady progress. Once rolling is complete, the automatic return cycle initiates. The rolls move back to their starting position, preparing instantly for the next billet. This repetition keeps production efficient and consistent. Watching the machine reset so seamlessly gives confidence in its reliability. The cycle finishes with a ring fully formed, ready for cooling and further processing. Each completed piece reflects both strength and accuracy achieved through automation. A stream of glowing steel leaving the furnace is always a striking sight, carrying heat and potential in equal measure. At Dahan Steel, that energy is shaped into rebars through a fully automated hot rolling line supplied by SMS Group. The moment billets reach the rolling stands, the workshop fills with power and rhythm. The billets, up to 155 millimeters square, enter the first mill section. A sequence of horizontal and vertical rolls reduces them into round feeders, each pass refining their profile. Electrical and automation systems keep the line stable, displaying every stage at the control station. Watching numbers, graphs, and signals respond instantly adds another layer of fascination. Next is the finishing block with 8 passes, where rebars take their final diameters between 10 and 20 millimeters. Quenching and tempering follow, applying water pressures up to 14 bars for hardening and up to 6 bars for controlled cooling. This stage defines the strength and toughness that builders rely on. High-speed shears trim head and tail ends at up to 35 meters per second. The rebars are then guided into the vertical compact coiler. Coils, weighing up to 2.1 tons, form tightly and are strapped for transport. Seeing them stacked neatly, glowing strength now tamed into order closes the cycle with impact. Strength on the open sea begins long before a boat touches the water. In this construction hall, a plate boat takes shape through welding, fitting, and reinforcement, resulting in a vessel designed for stability and durability. The first sight of raw aluminum sheets stacked together already promises something powerful. The process begins with thick 5 mm bottom sheets, forming the foundation of the hull. These plates are cut and aligned with accuracy before being fixed into place. Each alignment step adds to the feeling that the boat is growing stronger. Workers secure the base structure, ensuring that every joint will carry the heavy demands of blue water fishing. It feels as though every weld adds invisible muscle to the frame, preparing it for the relentless test of waves. Next comes the internal subframe rib structure, a skeletal framework that distributes loads across the vessel. Hundreds of welds connect ribs and plates, building resilience layer by layer. At this stage, sparks flying across the workshop create an intense and determined atmosphere. Over 500 meters of welding is applied to a single boat, locking the structure into a unified form. It is striking to think about the hours invested just to guarantee strength beneath the surface. This is not only construction, it is craftsmanship where endurance is written into every seam. Side sheets and transom sections are then attached, giving the boat its recognizable outline. Bracing elements are fitted inside, supporting the sides against the pressures of waves. Every addition seems to transform the hull into something more formidable. Finally, the finishing stage involves grinding, inspection, and protective coatings. By the time construction is complete, a vessel that once began as flat sheets now stands as a symbol of toughness, stability, and performance. The intense heat of a furnace holds the key to unlocking durability in stainless steel. The process seen here shows how industrial-scale solution annealing gives life to a massive SA-240 and 304 L vessel. Each movement is purposeful, and the environment reflects the intensity of working with extreme heat. The component, with dimensions T46X Idaho 6200 XTL50, shaped as a 2-to-1 elliptical head, is introduced into the furnace. The steel has undergone cold forming with 2 welded seam joints, and now it enters the stage that defines its durability. The size alone is impressive, making the operation feel monumental. Inside the furnace, the atmosphere rises steadily to 1040 to 1060 degrees Celsius. The vessel is held at this range for 46 minutes, allowing the microstructure to homogenize. The glow of heated steel gives a sense of both power and vulnerability. Once the holding period is complete, rapid removal follows. Immediate water quenching halts the process and locks in the desired properties. The rush of steam highlights the sheer violence of the temperature drop. The material's internal stresses are relieved, and corrosion resistance is enhanced. It is remarkable how steel, once brittle after forming, emerges stronger and more reliable. The vessel is now stabilized and ready for industrial use. This balance of heat and speed defines the very essence of controlled metallurgy. To one seamless outcome. Inside the factory, production flows through a sequence where each part matters to the final result. Every sound of machinery feels like a heartbeat, pushing the process forward with rhythm. First, the liquid paint is blended with solvents and pigments in large mixing tanks, ensuring consistency. Then, empty tinplate cans are stamped and formed, providing the sturdy container. They move along conveyors where valves and actuators await their turn. It is striking how a plain metal shell is destined to become a tool of creativity. Next, the mixture is filled into the cans with automated systems. The pace of filling lines shows just how efficient modern manufacturing has become. Afterward, propellant is injected under pressure to create the spray effect. Valves are mounted, sealing the contents securely. There is a sense of anticipation knowing the can is nearly ready for use. Finally, packaging completes the journey, making the cans ready for shipping. The finished rows of spray paint shine with promise, like colors waiting to be unleashed.
In the crash lab, vehicles accelerate into impact while digital simulations refine design. Airbags activate during trials, and engineers continually adjust models. The atmosphere radiates intense commitment throughout. Sirens pierce the air as the fire brigade rushes toward the accident site. A tractor lies overturned, blocking part of the roadway and raising urgent safety risks. Crews immediately secure the perimeter, setting up barriers to prevent further danger. The urgency in every movement is striking. Traffic is redirected, allowing space for rescue operations to continue efficiently. Such coordination highlights true dedication. Strong steel cables are connected to the tractor, and with the steady pull of a rescue truck, the vehicle begins to rise upright. Relief spreads among the crew as the heavy machine finally regains balance. At first impression, the claw looks like a mechanical giant designed for a single purpose, lifting what no other system can manage. Rebar developed this massive underwater lift device in only 8 months, a response to the challenge of reducing diver risk during salvage operations. Engineering came first, with teams designing two identical grappling structures, each 122 feet tall, 112 feet wide, and weighing 1,000 tons. The numbers alone give a sense of the enormous effort behind the project. These were integrated with the VB-10,000 lift system, allowing independent or tandem use depending on the weight of the recovery. It's fascinating how adaptability is built into something so massive. Fabrication followed, where giant steel jaws took shape in heavy workshops before being tested under strict load simulations. Every step seemed like preparing a creature of steel for the ocean. Once complete, the devices were ready for deployment offshore. The process of lifting required custom-engineered cradles, lowered to the seabed as stable bases for fragile topsides. This approach shows a clever balance between strength and delicacy. The claw then secured damaged structures and transferred them to the cradle before raising the entire package to the surface. Watching this sequence feels like seeing strength used with surprising finesse. The system's versatility allowed adjustments for each project, ensuring efficiency and safety. In recognition, it earned the OTC Spotlight on New Technology Award in 2012. Such recognition highlights not only engineering skill but also problem-solving vision. Hontrin,